So we are into applying the first law, conservation of energy, to reacting systems. And we need to talk about the enthalpy of formation, which you already have, the enthalpy of combustion, and then we'll be introduced to two heating values, a higher and a lower heating value. Then we'll go to the adiabatic flame temperature. We won't get as far as absolute entropy in third law. One thing is you can do combustion for a closed system. Let's just focus on open system combustion. Okay? So no problems on the final exam will deal with reacting systems in closed systems. Right? So it's all just open system analysis. So let's review. So we have the conservation of energy for a reacting system or open system. We have a combustion chamber. We have fuel coming in, possibly air or pure oxygen. We just need an oxygen source. And then we go out with the products, which are primarily carbon dioxide and water. And if there is nitrogen coming from air, then that'll come out as well. So you have the reactants and the products, and the sign convention is Q dot in positive. And you can write the first law for a control volume, and here it is written. So and then we divide by the molar flow rate of the fuel coming in, N dot fuel, and so you have the rate of heat transfer into the control volume per rate of fuel flow rate into the control volume. Then you also have any shaft work out. In all the problems I've seen, this is 0. But in general, you could have some work power out, right? But I'm trying to remember if there's any problems where it's not 0. But a high percentage, if not all the time, that term is 0. All right. Then what do we have? We have the sum over all the products, the coefficient in the balanced chemical reaction equation, times that enthalpy. That enthalpy is a function of primarily temperature and only temperature if it's an ideal gas. But if it's a non-ideal gas, then it could be a function of temperature and pressure. But often, again, H is a function of T only for an ideal gas. Well, so it's a function. This you could have written just here H bar as a function of T and P. And so it's made up of the sum of the enthalpy of formation and then the deviation from the reference condition for that gas. That reference condition is 25 degrees C, 1 atm, or 298 Kelvin, 1 atm. All right. So we have the enthalpy of formation at standard conditions. And then the departure. So if the products come out hot, this delta H bar will be the temperature of the exit minus the 25 degrees C, 298 reference temperature. Likewise, you have the sum over the reactants, the stoichiometric coefficient. That enthalpy is made up of an enthalpy of formation and then a deviation from the reference condition. All right. Let's continue on. Just as a reminder, in the table in the textbook, you have that enthalpy of formation given. Some elements have 0 values for the enthalpy of formation, nitrogen and oxygen. Why? Because they're stable at that temperature and pressure. That's what they like to be at. They like to just be at O2 and N2. The carbon monoxide, carbon dioxide have non-zero values, and they're typically negative, but not always. We're going to solve a problem with propane, and so here's the value of propane. So propane, C3H8, combusts completely with 250% theoretical air. Propane enters at standard 298, and dry air enters at 298, and products leave at a toasty 1000 Kelvin. Determine the rate of heat transfer to the combustion chamber in kilojoules per kilomole Kelvin. So our little combustion chamber, our fuel, our air, those are all our reactants coming out with our products. And we're interested in calculating this Q dot into the combustion chamber, and it's per kilomole of fuel, kilojoules per kilomole of fuel. So it's Q dot over N dot F or Q over NF. Either way, that's what we're asked to solve for. So we write the balanced reaction equation. First, get it to be still 100% theoretical air, and then we'll modify it for 250%. So start with the fuel. Leave a 1. Don't change it. Sometimes people don't even put the 1 in front of the coefficient in front of the fuel. We'll pick up the oxygen and in the right proportion the nitrogen from air. It'll go to complete combustion to carbon dioxide. At this point we can calculate the number of moles of CO2 just by doing a carbon balance. We have to have 3 CO2s. And then the amount of water in the vapor state at 1000 Kelvin, it's definitely vapor. And at this point we can even get the coefficient in front of the water doing a hydrogen balance. We see that H's only are in the fuel. There's 8 of them, so we have 4. And then at this point you can go back and get the oxygen balance for 100% theoretical air. That'll be 6 O's from here, 4 O's from there. That leaves 10 oxygen. So there's 5 O2s. Leave a little space to modify for 250%. Come over here. When we have 250% air, we'll have more oxygen coming out. But at this point, I need to just finish out the nitrogen balance. 3.76 times 5. And leave a little space right there, little space right there, and a little space right there. Now let's modify it. Now that we have it balanced for 100% theoretical air, let's modify it for 250. True? So if we come in and say 2.5, is that the correct coefficient here? 2.5? Thumbs up if you agree. Let's do the oxygen, or nitrogen's the easiest. 2.5. So we're good on the nitrogen. Nitrogen's finished. Now the hard one, the oxygen. So what is it? 5 times 1.5? What is it? Can you see it? Yeah, this is the hard part, isn't it? Anybody else? Do you see it? Right. So there you go. So there it is. Now it's balanced. That's our balanced equation for 250% theoretical air. Now we want to calculate this ratio, Q over N of F. So we write our first law, and so our Q over NF minus W over NF, which is just 0. True? Just get rid of that. We don't have any work coming out of this control volume around the combustion chamber. And then it's the sum over the products of the coefficient times that enthalpy on a molar basis minus the sum coefficients enthalpy of the reactants. Well, it's the sum over the products of N times the enthalpy of formation plus any change of the products. It's going to be enthalpy evaluated at the temperature exit minus the enthalpy evaluated at the temperature inlet on a molar basis. If you wanted to, you just say this is the inlet, or this is the exit, or you put 1 and 2 if you like subscripts 1 and 2. All right. I'm sorry, this is not inlet. This is reference. Right? Minus the sum of the products, the reactants, the coefficient, enthalpy of formation, the molar enthalpy at the temperature of the incoming, minus the enthalpy at the reference. Did I write that correct? Give me a thumbs up if you like it. 1, 2, 3, 4, 5, 6. Okay, looks good. Thank you. Now, remind me, what is this temperature? 298. This temperature, 298. If the propane enters at 298 and the dry air enters at 298, all the reactants are coming in at 298. That difference is 0. All right. Unfortunately or fortunately, this problem, it's exiting at 1,000 Kelvin. So I have to get the molar enthalpy of each of the products, the CO2, the H2O, the O2, and the N2 at 1,000. Likewise, the molar enthalpy of each of the products at 298, take that difference. All right. One thing that I can do to help is I can reduce not writing all these multiplications out. If I just do this multiplication, or let me rewrite my balance equation. I'm going to rewrite it. Let me do this. It'll be a little cleaner if I rewrite this balance equation. 1C3H8 plus exactly how many O2s? 12.5 O2s. What's 5 times 2.5? Is it 12.5? See where that came from? Good. And then you're going to have how many N2s? 47 N2s, or close enough to 47, goes to 3 CO2s plus 4 H2Os plus, we're going to have 7.5 O2s. Make sense? And 47 N2s. So now I have just a nice integer for the coefficients. All right. Now let's continue to write down here. So sum over all the products. I'm going to do the CO2 first. 3 times the enthalpy of formation of the carbon dioxide, negative 393,520, plus the molar enthalpy of carbon dioxide at 1,000 Kelvin. That one is going to be 42,769. A lot of table work. You got to get into the table and pull these values out. Minus the molar enthalpy of the carbon dioxide at 298, 9364. Close for the carbon dioxide. We add to it the number of moles of water vapor, 4. The enthalpy of formation for water vapor, negative 241,820, minus the enthalpy at 1,000, 35,882. I'm sorry, that's a plus. Then subtract the enthalpy at 298, 9904. We finish for the water. We go to the oxygen in the products. It's going to be the coefficient, 7.5, so it's a plus, times the enthalpy of formation for the oxygen, 0. The enthalpy at 1,000 Kelvin, 31389. The enthalpy at the reference, 8682, plus the number of moles of nitrogen in the products, 47, times 0 for the enthalpy of formation of the nitrogen, plus the enthalpy at the elevated 1,000 Kelvin, minus evaluated at 298. We finished the sum over all the products. Now we subtract for each of the reactants. We'll start with the fuel first. So the fuel has a coefficient 1, and it has enthalpy formation for the propane, negative 103,850. it comes in, and I'm just going to put them at 0, 0. So the change in the enthalpy is just 0, delta H. For the propane, it comes in at 25 C, which is the reference temperature. How about minus for the oxygen, 12.5, enthalpy formation, 0, plus, well, it comes in at 25 degrees C, so it's 0. And then I do the nitrogen in the reactants. It's going to be 47. The enthalpy of formation is 0. And the deviation from 25 degrees C is 0. So a lot of times there's a lot of zeros, which is good. So now we can compute our final answer. Let me just kind of put it right here. Q over N sub F is calculated to be negative 660, 941 kilojoules per kilomole. So there's our final answer. Sorry, I ran out of room at the bottom. I had to tuck the answer in the middle, but there it is. So what does the negative sign mean? It's really not into the combustion chamber, it's out. Trying to be consistent with our textbook. And it's per kilomole of what? Kilomole of the fuel, each fuel, propane coming in. Let me ask you a question. Well, let's continue on and we'll ask more questions. Well, we have this concept of the energy balance, which is repeated here. Didn't we just apply this equation and solve that previous problem? We also are introduced now to an enthalpy of combustion. This is on a molar basis, that's the H bar. On a molar basis, it's going from reactants to products. And it's defined as simply the sum over all the products of this H bar of the exiting products. That's this right here, H bar. And minus the sum over all the reactants, the stoichiometric coefficient, and this term, H bar, of all the incoming reactants. So basically, this whole side, whether it's any work or when it's any heat, is just called the enthalpy of combustion. Now, it's common to talk about the enthalpy of combustion at a standard temperature. So right here, put naught right there, meaning that the products and the reactants go in and out at 25 C. Then the left-hand side of the energy balance is equal to simply a sum of the coefficients times the enthalpy of formation of each product going out, and minus the sum stoichiometric coefficient times enthalpy of formation of all the reactants coming in. Okay, so this is a useful concept, this enthalpy of combustion, or standard enthalpy of combustion, if it's at the standard condition, 25 C, 1 atm. Compute this enthalpy of combustion at 25 C, or you could just say the standard enthalpy of combustion, in units of kilojoules per kilomole for the following: propane, methane, acetylene. So let's just pick one, propane. So the propane, you have to have an idea of how it reacts, because remember the equation, the enthalpy going from reactants to products on a molar basis, the standard enthalpy of combustion is equal to the sum over the products, the coefficient times the enthalpy of formation for each of those products, minus the sum reactant stoichiometric coefficient, enthalpy of formation. True? So I do need to have a good idea of the coefficients for the terms which have non-zero enthalpies of formation. So let me just kind of fit this in for propane. We'll start C3H8 plus, I don't know how much excess air, all right, goes to how many CO2s? The number of CO2s is dictated by the number of carbons in the fuel. And then it goes to how many waters? The number of waters is dictated by how many hydrogens are in the fuel. True? So the coefficient 3 and 4 doesn't change. We're always going to leave 1 in front of the fuel. Doesn't change. True? Okay. You just go ahead and say I'm going to have 100% theoretical error, so N2 3.76. Oh, I forgot to come back. That's 6, 7, 8, 9, 10. That's 5. And then 5. True? So if we write this out, we want to compute the standard enthalpy of combustion for propane. It'll be, for the products, 3 times the, well, let me do this, N H bar naught F for the CO2 plus N H bar naught F for the H2O plus N enthalpy formation, the N2 minus N enthalpy formation for the fuel minus N enthalpy formation for the oxygen and minus N enthalpy formation for the nitrogen. Okay? This nitrogen was in the products, this nitrogen was in the reactants. But which one of these enthalpies of formation are 0? The nitrogen. Are there any other enthalpy of formations equal to 0? The oxygen. So it really didn't matter if you had 120% theoretical error, because all that do was put some O2s over here and more N2s. But if you're computing the standard enthalpy of combustion, it's really the how much CO2 and its enthalpy of formation, how many H2Os and enthalpy of formation, how many fuels, that's 1, and the enthalpy of formation of the fuel. So if you put the numbers to it, you'll find it's 3 times what? Negative 393,520 plus 4 times negative 241,820 minus 1 times the propane's number we've written before, negative 103,850. All right? So that gives you a value for that fuel. Do it for methane. How fast do you think we could do it for methane? Pretty fast? Let's kind of just sketch it out for methane. You would have CH4 goes to how many carbon dioxides? 1. And how many H2Os? 2. Those are all the coefficients I need. I just need the fuel, the carbon dioxide, and the methane. And so for the methane, it would be 1 times negative 393,520 plus 2 times negative 241,820 minus negative, and for the methane, let me look it up quickly. For the methane, negative 74,850. And then you would do it also for the acetylene. Got to get the coefficients from the CO2 and the H2O, and then find the enthalpy of formation of each of those entities. I'll come back to that problem in a minute. Let's talk about heating value. Notice that the the enthalpy of the combustion was typically negative. Okay, look at all these negative values. It's for the propane, negative 2,043,990 kilojoules per kilomole. And then for the methane, I'll just scoot down a little bit, was negative 802,310 kilojoules per kilomole. The negative sign indicates it's heat transfer out of the combustion chamber. It's, as you might expect, very exothermic reaction, burning of fuel. So that's what the negative sign is. Now we talk about a heating value. We like to work with positive values indicating the magnitude of the standard enthalpy of combustion, and we have it on a mass basis, not on a molar basis. So we're looking for a positive number for how much heat is released in the combustion of that fuel. Propane has a different heat release than methane, than acetylene. Okay? And you have two heating values. You have the lower heating value and the higher heating value. I'm going to do this. I'm going to talk about the lower heating value first. And the lower heating value is when H2O goes out in the gas, just like what we had. Okay? So before, for the propane, we had a value for this standard enthalpy of combustion, true? If we want to calculate a lower heating value, first of all, get rid of the negative sign. And now it'll be how many kilojoules, just chasing units, how many kilojoules of heat release per kilomole of the fuel. That's the units on this term. If I now multiply or divide by the molar mass of the fuel, what's the molar mass of the fuel? It's how many kilograms of the fuel per kilomole of the fuel. We see that the kilomoles of the fuel cancel, true? And we're left with a positive entity, how many kilojoules of heat are transferred out, standard combustion, per kilogram of the fuel. And so that's our lower heating value. So the lower heating value is negative times 1 over the molar mass of the fuel. Okay. Now, what about the higher heating value? Well, the higher heating value is when the product, the water vapor in the products, goes out in the liquid state. It's more common for the water vapor to go out, or water to go out in the vapor state. But it could come out of that reaction combustion chamber in the liquid state, or some of it could, but let's assume now all of it goes out in the liquid state. When it all goes out in the liquid state, think about it in two stages. This H2O out in the vapor or the gas state, and now it's H2O out in the liquid state. Okay, you have to have a heat transfer into this zone or chamber or control volume, true? And it's going to be removing heat, Q remove, per molar flow rate of the H2O. Or, let me ask another question, the heat removed per mass of the H2O. How much, if this water vapor is coming in at 25 degrees C, and it comes out of this control volume at 25 degrees C, but it's liquid, how many kilojoules of heat have to be transferred out of that control volume per kilogram of water coming in? See what we're asking? How many kilojoules of heat have to be transferred per kilogram of water that's condensed in the control volume. It's going to be HFG. It's that heat of vaporization at 25C, which is right at 2400. It comes straight out of the steam tables. That makes sense? And so now you think about, here was the combustion, you had the reactants going to products. The rest of the products just go for the ride, but the one product of interest is water condensing. So you have this heating value, the lower heating value, added with this additional heat transfer to make the higher heating value. So the higher heating value, the equation to compute it, is going to be the lower heating value plus how many, because this is, look at the units on it, it's how many kilograms of fuel, true? So what I have to know is I have to know the kilograms, thinking of units, the kilograms of vapor per kilogram of fuel, and if I multiply that by how many kilojoules of heat have to be transferred, looking at units only, per kilogram of vapor, then I'll get the units to work. So what we have is we add to the lower heating value, you add this, what's this? Kilogram of vapor per kilogram of fuel. Well, it's the mass of vapor per mass of fuel, or the number of moles of the water, H2O, times the molar mass of water, H2O, divided by the number of moles of the fuel in my balanced stoichiometric equation, which is 1, we leave a 1 there, times the molar mass of the fuel, times HFG. And there's your equation. That's how you jump back and forth between the lower heating value and the higher heating value. The higher heating value is going to be greater in magnitude. Both of them are positive. So if we come back to the propane, you say, okay, what was my balanced equation again for the propane? You do it so many times you kind of get tired of it, right? You said C3H8, and it went to how many H2Os? 4. Went to 4 H2Os. So for every mole of fuel, I have 4 water vapors. So in this case, it'll be the lower heating value plus the number of moles of H2O, 4, per number of moles of fuel, 1. The molar mass of H2O, 18.02. And then the molar mass of the fuel for propane, I have it written down somewhere. 44. Somewhere 44 something. True? 44.0 something. All right. And then you multiply by the enthalpy, the heat of vaporization at 25C for water, which is, would you say, 2442 kilojoules per kilogram? And that works. All right. If you change to a different fuel, let's say you burn acetylene, C2H2, right? Well, how many moles of water are produced per mole of fuel burned for acetylene? 1. And so this equation going from the lower heating value to the higher heating value, that coefficient right there changes, and the molar mass of the fuel changes. But the HFG stays the same. So here are the values for the heating values. They're in that table A25. You can see they give you the higher heating value in kilojoules per kilogram and the lower heating value in kilojoules per kilogram. And you can take a look at different fuels, methane, acetylene, there was that acetylene, propane right here. And you can compute these two numbers and compare them. So here's the problem that we should work. So it says compute the lower heating value and the higher heating value in units of kilojoules per kilogram. Is that per kilogram of the fuel? Is that what that kilogram is? Yeah, it's the kilogram of the fuel for the following: propane, methane, and acetylene. Here we give you the standard enthalpy of combustion for the propane, methane, and acetylene, and the molar mass of each. So to calculate this lower heating value, how did we do that again? Use the minus on the enthalpy, standard enthalpy of combustion to make it a positive entity. Then we divide it by the molar mass of that fuel. So 44, 16, 26. And there you go. So you would just fill in, let me fill in some of these numbers for lower heating values. 48,218. That's how many kilojoules of heat would be transferred out of the combustion chamber if you just burn the propane, and reactants and the products are all at standard temperature 25°C. How about for the methane? Oh, but also the propane, all the vapor comes out in the vapor state. I mean, all the water comes out in the vapor state. Okay. If you then use compute the higher heating value, what was that equation again? Well, it's going to be the lower heating value plus, then you have the stoichiometric coefficient of the vapor, the molar mass of the water vapor, stoichiometric coefficient of the fuel, which is always 1, hopefully, and then the molar mass of the fuel times the enthalpy, heat of vaporization, HFG for water vapor at 25°C. Anyway, for the propane, you find this is 49908. So it's greater. So somewhere in between is reality, because you probably aren't going to get all of that unless it comes out hot. If it comes out cool, some of that it could be below the dew point temperature of the products, and water would like to condense. Okay. How about the methane? We can flush out this table for the methane. It's 50019, and it's 55507, and for acetylene 46359 and 50352. Okay. So those are your higher and lower heating values. All right. Let's talk about adiabatic flame temperature. So what we do is you have your combustion chamber, and do we allow any Q dot? By the name, adiabatic, so it's set to 0. So it's a well-insulated combustion chamber. You have your fuel, you have some air or pure oxygen, whatever it is, you have some O2 coming in, and then out go the products. In this case, the temperature of the products will be high. It'll be the highest possible. All right. And so they talk about the temperature of the adiabatic flame temperature being that highest possible temperature of the products. Typically you have this 25°C. You don't play around with, oh, if I bring it a little warmer, well, yeah, it's going to be a little warmer going out. But it's dictated by that heat release, how much energy is released per kilogram of the fuel. All right. So let me jump back and grab a balanced equation. Go back even further. Let me grab this equation right here. Whoops, I don't know if I can now. Yeah, I think I can. Or maybe I want a better equation. Let me grab it, and if I don't like it, I'll come back and get another one. Okay, let's do it for this propane. Yeah. Okay, we'll use this equation. Edit, paste. So in general, you have nothing, no work, that's 0. The products, this is coming out large, a large delta H, because it's H of the adiabatic flame temperature minus H at the reference temperature of 298. The reactants, bring them in at standard conditions, 25 degrees C. So what happens is if it's adiabatic, this term is driven to 0. And how do you compute the adiabatic flame temperature? Is by slowly computationally increasing this temperature until this equation is equal to 0. The right-hand side is equal to the left-hand side. That's tedious. You need to do it. You need to do it by hand a few times so that you know how to do it. Usually you kind of jump up in temperature and you make this right-hand side a bracket 0. One time it's positive, one time it's negative. And then you use a linear interpolation to get the next best estimate of temperature. And do that again to try and drive the left-hand side equal to the right-hand side, and the left-hand side needs to be 0. Okay? It's a little tedious, but it can be done. The best way to do it is solve a problem like this. So it says compute the adiabatic flame temperature of propane with 250% theoretical error. We did this one already, 250% theoretical error, true? So let me go back and grab this equation right here. All right. Edit, copy, jump all the way back here, edit, paste. All right. And so what was on this side? It was Q over N of fuel, true? And what we want is we want this now to be 0 if it's adiabatic flame. So what's going to happen is the CO2, that has to be changed. This is the molar enthalpy of CO2, and it's going to be evaluated at that adiabatic flame temperature. This value stays the same. That's the molar enthalpy of CO2 at 298. And this value stays the same. It's the enthalpy of formation of CO2. True? All right. This stays the same. That stays the same. This changes. It's the molar enthalpy of H2O vapor at some unknown adiabatic flame temperature that you guess and iterate. Likewise, what is this? The enthalpy, molar enthalpy for nitrogen. No, that was for oxygen. Oxygen at the adiabatic flame temperature. And this one is the molar enthalpy of the nitrogen at the adiabatic flame temperature. The rest of these values, like the enthalpy of formation of my propane, enthalpy of the enthalpy of 298 for oxygen, enthalpy of 298 for nitrogen, they all don't change. So you start to increase the adiabatic flame temperature. And for this problem, the adiabatic flame temperature can be computed for propane with 250% theoretical error to be around 1300. I think the adiabatic flame temperature was around 1303 Kelvin. Yes, sir.
There's no way to do dimensional analysis and not go through the iterations.
Dimensional analysis? I don't see how that would help. Well, I could show you quickly in Excel. I mean, I solve almost all this stuff in Excel, right? Because it becomes super tedious. True? This is super tedious. But here is that problem in Excel. All right? So you can see I first have a line for propane, oxygen, nitrogen, carbon dioxide, water, oxygen, nitrogen, all for theoretical error, and then I balance it for 250 and I get the coefficients, 12.5, 47. So then I have to put all my ins, all of my reactants, propane, oxygen, nitrogen, put the enthalpy of formation, some of them are 0, inlet temperature, evaluate that enthalpy. That's just a call to a routine to evaluate that enthalpy as a function of temperature. Let me show you. See that? It's just H underscore T underscore O2. That's available. I know that one is available on our computers in the engineering. And then if you can do the delta H, but here for this problem, Tn is equal to Tref 0. And then you do the coefficient times H of F times delta H. Then you do the sum over all of the inlets, all the reactants. Then you do each product, CO2. Well, what's the coefficient? You just bring that down. What's the coefficient? Bring that down. And then likewise for O2 and N2. The enthalpy of formation, unfortunately, you just have to put that in by hand. But if you had this temperature, the products come out at this temperature. So if I change this to 1200, it's going to basically change it because it copies it down, right? Compared to the reference. So I evaluate the, that should be H2 right there. The enthalpy at the temperature, 1200 Kelvin, I can get all those calls. See, like CO2, then the call for the H2O vapor. So I then do the multiplication, do the sum. And this Q is the difference. It's the sum minus of the products minus the sum of the reactants. True? All right. So now I have this value. If I change it to 1300, it reduces Q. I want to drive that to 0. In Excel, you would go to data. In data, go over to, there's a couple ways of doing it. What if, goal seek, says take this cell right here, which is cell C18. I want to make it go to what value? I want to make it go to 0. By changing what value? By changing this cell right there. And then I hit OK, and boom, it changes it to 1303 Kelvin. So how many people remember root finding in your numerical methods class? Newton-Raphson, secant, bisection. Those create any nightmares? Any, you know? Well, here it is in glory in Excel. So you don't have to start off anywhere close. Let's say we started off at 500. This is far from 0, but I come to what if, goal seek. I want that to be driven to 0 by changing that cell, and it goes to the same answer. Thank you for your attention. We're all done.